getting recorded. Okay. Okay. Hi everyone. Good evening. So today's talk is on extremal graph theory. So I plan to discuss some theory today, and maybe we'll see some solutions to some contest problems tomorrow. So like uh, firstly, in extremal graph theory, we will deal with problems of the form. Also, yeah. So I will not be keeping up with the chat. So if you have any questions, just unmute yourself and ask. Okay. So in extremal graph theory, we'll be dealing with questions of the form like suppose you are given a graph G with say n vertices. Okay, and what's the maximal number of edges that you can have such that G does not have a known subgraph H. So to just put that into perspective. So suppose, for example, if I ask you, you are given a graph with n vertices, uh, what's the maximal number you can have to say avoid a cycle? So that would be just like n minus 1 edges, right? And the construction would be just take a tree. So it's kind of well known, like if you have n edges, then you always have a cycle. So for in this case, if H was just any cycle, then we saw that to avoid any cycle, you can have at most a number of vertices minus 1 number of edges. So something we are going to be very interested in general in this topic is clique avoidance. Clique means basically a complete graph on n vertices. That's n clique is basically a complete graph on n vertices. So something like a K4 is something like you have 4 vertices and draw all possible edges. Yeah. So yeah, so we are going to be very interested in clique avoidance problems in general. And apart from that, before I mostly talk about proofs of theorems today. So some general heuristical approaches you can have in mind before you start reading extremal graph theory in general is first thing, it's combo after all. So general combo stuff applies. Apart from that, you will have you will be applying global ideas. You can at some point you might have to be dealing with sums of the form, let's say uv edge f of u comma v for some function uv, or something like v belongs to the fv, where okay, so sums of this, you have to be dealing with sums of this form, where say a function of just vertices, or a function of uv where uv is an edge, or similar. Another thing is local ideas are also going to pop up a lot in this part. So for example, what I mean by local ideas is you might have to look at a special structure in the graph, and these are mostly motivated by uh, the equality case. So another thing is very important for most extremal graph theory problems. You'll probably have to find the equality case first. This motivates a lot of stuff. This will tell you what structures to look for, how to go about the proof, etc. Another thing is finally is induction. So induction is it really works well with graph theory in general, because a graph minus a vertex or an edge is still a graph. So yeah, so this is just some basic ideas that you might have to keep in mind, and these are going to be recurring themes in the proofs I'm going to present, and even the problems after. Okay, so first theorem we are going to discuss about, the first topic is just triangle avoidance. So we are dealing with the question suppose G has n vertices, what's the max number of G can have given G has no triangle? So,
Yeah,
hello? Yeah, is there a question?
no, sorry.
Okay, cool. So given G has no triangle, what's the maximum number of edges G can have? So it turns out this uh, Mantle's theorem gives us the answer. And the theorem tells you that if mod V equals, if cardinality of V is and its n vertices, then uh, if G is triangle free, we'll use the word triangle free to mean like no triangles. Then that means that G has at most floor of n squared over 4 by n squared over 4 n squared over 4 edges. So this is the Mantle's theorem. So for example, for something like n equals to 4, that would be like you can have this graph, right? So this graph has like 4 edges, but no triangles, right? So like now what happens if you add an edge? So something like this, right? So you see like 5 edges, this has 5 edges and has triangles. So this doesn't work, right? So similarly, you can like see like for n equals to 4, the max hashtag edges is just 4 square over 4. That's 4. Okay. So I'll present two proofs of this theorem. So the first proof is going to be like just more of an algebraic proof. So okay, let's see. So consider any edge, right? So consider any edge uv. So now think about this. Like if u and v have a common neighbor, let's say w, then uwv would be a triangle, right? So you come to the conclusion that if uv edge u comma v have no common neighbors. Okay, so like now think about the edges that emanate from u and from v respectively, right? So let's say this. Okay, so this is, we'll call this the neighborhood of u. That is, neighborhood of u actually is all the vertices that are adjacent to u. So this is basically neighborhood of u minus v sort of, and this is also similarly neighborhood of v minus u. This is a notation we will use a lot. Nu refers to set of vertices. So now think about this. Like we know that they have no common neighbors, right? So a direct implication of this is like these two sets like cannot intersect, right? So the cannot intersect condition can be like nicely formulated by just writing. So how many edges are here? So this have like degree u minus 1 vertices are present in this set, right? And similarly in this set, degree v minus 1 vertices are present. So you can kind of write, if you like look at their they cannot intersect, right? So that means like a direct implication is like this value should, because this is the worst case sort of like if you had, if it was more than this, so suppose it were like 5 vertices here, right? uh okay, sorry, just let's erase that. So suppose there were like uh 5 vertices here, and suppose this was your u and this was your v, and suppose there was a common neighbor, right? Then if the if this condition doesn't hold, then basically you can just do the, I think you can just use this sort of to get that a common neighbor must exist, right? I'll just leave the details. So we find that if uv is an edge, then this condition holds, right? Otherwise, if this is not true, then you'd end up with a common neighbor. So this basically rearranges to write degree u plus degree v is at most n for all uv edge. So what we will do is like we will just sum over all edges. So this is also a global idea, sort of sum over all edges. So let's say the number of edges is m, right? So then what we find is something like mn is summation uv edge degree u plus degree v. Okay. So now, like, think about this. This sum is sort of hard to deal with. So how can we like make this into a more uh, tame form, sort of, so that it can be easier to work with? Think about this. Like in this expression, okay, you have something like, how many times does degree u get counted? Degree u gets counted every time there's some v such that uv is an edge, right? So now there are like degree v. In other words, the degree u term in here gets counted degree u times. So this is really, so these two summations are basically equal. Does anyone have any questions regarding this? How I am like changing the sum, sort of?
What about
Okay.
the degree V?
Yes.
What about the degree V term?
Yeah, but you can just like think about them separately, right? Like degree v also gets counted whenever there is a u such that uv is an edge. So like doesn't like really affect the final thing, as they don't really talk to each other. Does that make sense?
I think I'll just read out what somebody has written in the chat.
Sure.
So Dikshit says, we can still have a graph without triangulation with a neighborhood vertex, right? If and only if it's incident on the edge connect. Yeah, it's probably best to just read it.
We still have a graph without triangulation with a neighborhood vertex if it's incident on the edge. I don't really get what that means. Does that mean, do you mean to say something like you can have a u here, a v here, and a w here, and is that what you mean to say? That is just fine, right? Because this is just like nv bar u. So
Right. So if an vertices is lying on the edge, like we have some edges and we make some like we incident all the vertices on the connecting 2 points, like we take some
okay.
extremal point,
I
and like we
don't.
can
Do you
still
mean
have
like?
a
Do you mean something like u v w, something like this?
yeah, we can still
No, no, no.
transform it and
No, no, you are not. We are not doing that. We are not doing that. It's like draw the vertices. You are drawing out every edge like nicely, sort of. You, yeah. So like, yeah. So like, we are not dealing with any issue of collinearity here. Okay.
okay.
You cannot have any notion of collinearity in this thing. Okay. So once we get till here, it's kind of easy. From here we are just going to use Jensen's inequality, because the x square function on the x square function. Yeah, so using Jensen, you can sort of just write it as summation u belongs to v. There are n vertices. So sorry, I'll just move to the next page, I think. Yeah. Yeah, so we had like something like mn was at most summation uv edge degree u plus degree v, which becomes summation v belongs to v degree v whole squared. Okay, so using, now we can just write this is This is Jensen on x squared. Right. So Jensen is also some, you will have to use Jensen a lot in this kind of problems in general. This is basically convexity. Okay. And then this is what? This is basically n times degree of summation of degree v is just 2 times the number of edges. Right. So you come to something like mn is at most 2m by n whole square. And if you just like rearrange it, you get, yeah. So this is what we wanted to prove as desired. So any questions regarding this proof?
No.
Okay. Okay, I'll go with that. Okay. So now think about what we did in this proof. It was rather sort of algebraic, because what I mean by algebraic is like to find the optimal case, you would have to like set all variables to their equality cases and so on. Right. So this is kind of boring, right? And hence, in other words, we find that like this proof doesn't really give you a lot of insight into the equality structure. So we'll move on to a different proof, which is going to be nicer in the sense it will give us some idea about how the equality, the optimal case should look like. So proof 2. So the proof will begin with so first of all, notice that consider any vertex u, right, and look at its neighborhood. So suppose this is the neighborhood of u. Note that you cannot have any edge inside the neighborhood, because if this was an edge, then this would, suppose this is A and this is B. Then if AB was an edge, then you would have AUB triangle. So there is no edge UB, right? So in other words, for all vertices V, NV must be an independent set. This makes sense, right? Because if you have an edge inside NV, then this is basically forming a triangle. So this basically tells you that independent sets are important because they are coming up a lot, right? Every vertex kind of induces an independent set. So what we will do is we will pick the maximal independent set . So now think about this. This is a kind of a local idea because like you are dealing with a specialized structure right now. Okay, so now what does maximality give you really? So maximality basically gives you like if you add any V to U, right? So if you add V to A where V was already not in A, then A union V isn't independent anymore. Not independent anymore. So what are some implications of? Think about it, like every vertex induces a sort of independent set, right? Because you know that NU is always independent. So by maximality, you know that the value, the size of NU for any U is like at most A, right? So this basically tells you that degree U is at most A for all U belongs to V. So this is quite powerful. So also think about it, like suppose this was A, right? So suppose this was A and this was say the graph minus the vertices minus A. Suppose this was B, right? So here B is basically V bar A. So think about it, like you know that A is independent, right? And B, so you know that for all B belongs to B, there exists an A belongs to A such that AB edge. Why is this true? Because like if there was some vertex small b in the set capital B such that B is not neighbors with any vertex in capital A, right? Then you could just add small b to the set A and that would like and yet have an independent set, right? So that would contradict maximality of A. Right. So this basically tells you that for all B, there is some, for all B in B, it has some neighbor in A. Right. Another thing, note that since A is independent, every vertex, every edge must be adjacent to some b in B. This is trivial, right? Because like you cannot have an A to A edge. So you must have some vertex in B. So the edges can be of the form, so this cannot happen. Edges can be of the form B to A or of the form B to B. Right. So what we will do is like we'll again use a very trivial bound. So suppose number of edges is M, right? So suppose this was B and this was A. So think about, there are like two kinds of edges, right? Those are like edges from B to A and edges from B to B, right? So look at this quantity. So look at this quantity, right? So this is going to count the edges between B to A plus 2 times the edges between B to B, right? However, in any case, this is at least the total number of edges, because this term is non-negative, right? So we can just write something like, suppose M was the total number of edges. This is at least you know that this holds, right? Degree U is at most A. So from
Aryan,
here, yeah.
Your voice froze for the last 30 seconds or so.
Oh God. Okay, is it good now?
Yeah, it's good now.
Okay, I'll just repeat what I said. So like we were investigating the quantity summation B belongs to B degree B. Oh, okay, kind of addition and error. So note that this quantity tells you the number of edges from B to A plus 2 times the number of edges from 2 times the number of edges between B to B, right? Because this edge gets counted twice, sort of. Okay, so in either case, you know that this entire quantity is at least the total number of edges. Why at least? Because like this quantity is always like at least 0, right? So we'll just use this inequality. So you have something like, if number of edges is M, then you can write M is at most summation B over B belongs to B degree B, right? So now you know that degree B is always at most degree A. We saw this here. Right, we saw this here. And so basically just using that, this is what? This is just mod B into mod A. And then you can just use AMGM to get something like, this is at most, and this is mod A plus mod B is N, right? So this gives you N square over 4. So yeah, that also proves the theorem. So any questions regarding the proof of this, like this proof?
What is the motivation?
Okay, for this proof, you like, first of all, you start off with an observation that for any vertex U, its neighborhood is necessarily an independent set, right? So this basically kind of tells you that independent sets are quite important for the problem, and hence we pick like the maximal set. So since we are picking since we are adding a condition maximal, it gives us a lot of restrictions sort of to work with, and gives us
Why
a lot
would
of
anyone
properties
think
about
of
it.
G minus A?
Because you are working with,
That's a
you're working with the
non-trivial
entire.
step.
No. Something like, you know that A has like, where did the pen go? Yeah, you know that like A has no edges between itself, right? So there are no A to A edges, right? So all the edges in the graph must come from the other vertices, right? So like if the other set of vertices was B, you would always like the edges are coming from basically B to A or B to B. So that is basically how you get that is how you think about that. Any other questions? If there are no other questions, I'll just move on. Okay, so now this proof is going to tell you a bit about the equality structure. Equality occurs when like, okay, so like equality, for this we have kind of assumed that mod A is equal to mod B, right? So obviously, well, first of all, let us solve for n equals even. So equality occurs when the sizes of A and B are equal, number of edges is equal to summation of B belongs to B degree B. Basically, equality holds everywhere, right? And degree phi equals to A for all phi belongs to B. This is something we have just used, right? So it turns out like if you sort of put this all together, then the equality graph is just is kn over is the complete bipartite graph with every partition equaling n equals 2. So what I mean by kn comma 2 by n comma 2 kn by 2 comma n comma 2 is something like, suppose you have n equals 6, right? So this is basically this. So you have two partitions, it's a bipartite graph. You have two partitions, every partition having 3 vertices, and you draw all possible edges between them. So this is k3 comma 3. So this proof obviously doesn't like, so it turns out like you can modify this argument for n odd, and I'll just leave the equality for that. And it turns out that equality for n odd is k n minus 1 by 2 comma n plus 1 by 2. Okay, so it turns out like in general, the equality case is k floor of n comma n by 2 comma ceil of n by 2. So this is the equality structure in general for a triangle phi graph having maximal number of edges. So any questions relating to this? Do you understand what a complete bipartite graph means, right? So like you have basically two partitions, these like these and these, the two partitions are independent sets themselves, and you draw all possible edges between them. Okay, so are there any questions?
No.
Okay, let's move on here. So now let us think about how to solve the general case, right? General case is like we were avoiding, last problem was K3 avoidance. So now we are going to deal with a general arc plus 1 click avoidance. So we'll deal with now KR plus 1 avoidance. Right. So now think about the equality structure. The equality structure in the above proof. In this, sorry. So this was basically for R equals 2. There was a K3 avoidance. We had a two-partite graph, right? And what was complete two-partite graph? Complete two-partite graph. And what was special about it was also like partitions had almost equal size. What I mean by almost is like for the n even case, they were like same size, right? But for the n odd case, they used to differ by like 1. So motivated by this, we will make a guess for the KR plus 1 case. Right? What will be the guess? The equality structure.
A two-partite graph is basically you are dividing the graph into two partitions, right? Or not?
Aryan, are you there?
Yeah, right. Similar cases here, and for it to be a complete three-partite graph.
Actually, I don't think you were audible for the last 30
You
seconds.
froze.
Yeah.
I'll just repeat what I said. So like, yeah, for I was just describing what a R-partite graph was. So for R-partite graph, you need to have like R partition. So for R equals to 3, for example, so you have like 3 partitions here and some vertices here. Okay, and for it to be a complete three-partite graph, you need to have all possible edges drawn, right? And you cannot draw edges. It's going to be just too messy. Just draw everything sort of. So basically the idea is like you cannot have any edges between the vertices of the same partition, and for it to be complete you have to draw all other possible edges. So we will take a guess that the equality structure, okay, 1 second. The equality structure should be an R-partite graph. R-partite graph. Should be a complete R-partite graph, sorry. Complete R-partite graph. This is motivated from the R equals to 2 case, right? Also, another thing is sizes of the components or partitions or whatever are almost equal. What do I mean by almost equal? Different. So it turns out like you can formalize what I just wrote above, and turns out for every like n comma r, you have a unique graph which is called the Turan graph. Which is defined as follows. So what I just said about our guess for the R+1 case, k R+1 case. So Turan graph basically tells you the definition of the Turan graph is something like it is a complete R-partite graph, say k S1, S2, SR, where S1, Si is the size of every partition. Right. And Si equals to n over r floor or n over r seal for all I. So this is the Turan graph. You'll call it like Tn comma r for now. And this is unique for given n comma r. Right. Another thing I'll like just state as a sort of a fact here, which you can like sort of try to prove yourself over all R-partite graphs with n vertices. The Turan graph has of max edges. So you can try to prove this by say something like AMGM or something like that. Is not very interesting. I'll just leave it to whoever's attending. Okay, so this was about the Turan graph. So what we did was we guessed that for KR+1 avoidance, Turan graph was optimal. So convince yourself that the way the Turan graph has been defined, it can never have R+1 click, because you have just like R partitions, right? So, and you are just drawing all possible edges between them, right? So you always, so every vertex has degree of every vertex is always just R. So you can just never have the degree R+. Sorry. So okay, one thing. Okay, I messed up. So the degree of every vertex is just R-1, because it's in a partition and it can like give edges. So, sorry, it's R-1. So it is giving out edges to like R-1 vertices, right? So okay, just okay.
There are two vertices in the same set by pigeonholes,
Yeah,
and they can't be connected.
I kind of messed up. I'll just tell you. I'll just repeat what I said. So like in a Turan graph, you have like R partitions, right? So you're kind of drawing all possible edges from here to here to here and here to here to here. So you can like kind of see like the maximum click you will find in a Turan graph is just R, right? The R size click. How? Like just take a vertex here, take a vertex here, they're connected because complete, take a vertex here, again connected, and take a vertex here. So you can like never have a, so you can never have R+1 click in Turan graph. Convince yourselves that this is true. Maybe draw out a few, might help. So now, so our guess was like for the R+1 case, Turan graph was optimal. So Turan's theorem basically tells you that the guess is right. Okay, so Turan's theorem the guess is right. So if number of vertices is n and G is kr plus 1 free, then number of edges of G is at most number of edges of the Turan graph n comma r. Also, you can kind of prove that this value, right, E of T of n comma r is at most n square over 2 by 1 minus 1 over r. I'll leave out the proof for this is like quite easy to prove. Like you can just try to do it by yourself. The proof for something like r divides n. So for r divides n, right, what is E of T n comma r? It is just summation of vertices into degree by 2, right? So there's n vertices, each having degree nr times r minus 1. I think that's how you do it. Sorry. Okay, so it is n by r, right? Yeah. So there are n vertices, and there are and like each one of them have degree n by r times r minus 1, because there are r minus 1 partitions and n by r terms in every partition. So this is n square over 2 to 1 minus 1 by r. So for r divides and do it yourself, or like it's kind of boring. So this holds basically. This is what's important. So I'll actually present like 3 proofs for Turan's theorem. So each one will have like a different idea underlying the underlying idea. So like if anyone has any questions till this point, please feel free to ask. If there are no, I'm audible, right?
Yeah, you're audible.
Okay, cool. So I'll just like go to the proofs now. So the first proof I want to present for this is inductive proof. So what we will do is like suppose G is kr plus 1 free, and G has maximum number of edges possible. So what I mean by maximum number of edges possible is like if you add another edge to G, it now has r plus 1 click. Okay, so obviously G must have a r click, right? Why? Because if it doesn't, you can just add enough edges to make it have an r click. Otherwise, it could just like, because of max edges, really, it must have an r click. So what we will do is let A denote the kr in the graph which exists, and let B denote the rest of the vertices. Right? Okay. So now think about this. Yeah, 1 second. Yeah. So suppose this was A. And suppose this was B. And suppose this is a vertex B, small b in B, right? So think about how many neighbors B can have in A. So think about this, like if B has R neighbors in A, in other words, if B is connected to all of them, right, then you could just take A union B would be a r plus 1 click, right? So you can't allow this to happen. So what we know, what we just saw is like if B, as there is some vertex small b in capital B such that B like B has edges to all the vertices present in A, then you find that kind of violates the r plus 1 free condition, r plus 1 click free condition, right? So this is so this basically means that for all B belongs to B, at most r minus 1 edges in R, at most r minus 1 edges in. Also, like, yeah, I mentioned it previously. So we are dealing with, like, we are using an inductive approach, right? So we assumed kind of like it's true for less than n vertices graphs. Also, there's also I forgot to mention, there's like a trivial case where n is less than r, and that's like a trivial case because that is just a kn, right? That's a kind of trivial case. So whatever we are proving is like for n is at least r. I think you can just take n greater than r here. Whatever we are proving is for n is greater than r, because that's like the non-trivial case, right? If you have n is at least at most r, then you can just take the complete graph on n vertices and you would be fine. Okay, so does everyone follow till here? So we found that if there is a vertex b in capital B, it must have at most r minus. So every p belongs to B has at most r minus 1 neighbors in A. So now what can you say about the number of edges in G? The number of edges in G would be like edges from A to A edges plus A to B edges plus B to B edges, right? So A to A is just R choose 2, right? Because that's a complete graph. Now this, we found that this is like, it has like, okay, you can just use a, this is like at most n minus r times r minus 1, right? Because every neighbor, every B belongs to B has at most r minus 1 neighbors in A. So, and there are n minus r vertices in B. So this is, so this term makes sense. And then number of edges from B to B. Note that B, you can view B as like a graph on n minus r vertices, which has no r click. So that would just be by induction hypothesis, that would be n minus r, comma r. Now I claim that this value is equal to E of t of n comma r. Does anyone directly see why this is true? Okay, so okay, let's see. So I'm claiming that this sum of these three terms is equal to E of t t comma n E of t n comma r. So how to see this is like, so take t n comma r, right? Choose a vertex from every partition, right? So these vertices form a R click, right? So let A equals to this and let B denote the rest, like in the Turan graph, basically. So it's kind of similar because like this also similarly denotes the A to A edges, and this denotes the B to A edges as defined here, and this again like denotes the B to B edges. So you can see somewhat like this, that this term equals E of t of number of edges in t n comma r, right? Any questions regarding this? So this completes the proof, right? So this concludes. So any questions regarding this proof? Okay, I'll just check the chat anyway. Okay, since there are no questions, I'll just move on. Okay, so for this proof, we adopted an inductive approach. We saw that like the r less than n, n at most r case was trivial. That was just a kn would be a construction, and we assumed that the theorem was true for all graphs on less than n vertices, and then we proved it for n. So how we did it was like, since n, so we considered a graph which was kr plus 1 free and had maximum number of edges possible, which means that if you add any one edge, it will result in a graph, it will result in a kr plus 1. So by maximality, you must have a kr inside it. And so we let A denote the kr and B denote the other vertices. right? So it turns out like if you consider a vertex in the other part, it can have at most r minus 1 neighbors in the kr. Otherwise, you would end up having a kr plus 1, right? So using that, we just bounded the number of edges, and we found that it was equal to etn comma r, which concludes the proof, right? So, okay. How do you derive the equality case from this? So what we did was we proved that Turan graph implies equality. Now we need to prove that to prove equality implies Turan graph. So this is kind of simple. I'll leave out the details. So like you can just note that suppose your A was say V1, V2 up till PR, right? So you let's say you denote Ni equals N of V1. So this is basically the neighborhood of. So so N V1 here is not just the neighborhood of V1. So this is neighborhood of V1 in B. Okay. So this is how you're defining Ni. It's not like the natural. You can just call it N dash or something if that suits you. So for equality, you need all Ni's to be disjoint. Just check this yourself. This is not very hard to see. So this results in an arpatite graph. Right. And we know that we also know a fact that across all arpatite graphs with n vertices, Tn comma r has max hashtag edges. Yeah. So these two kind of combine to tell you that equality implies Turan. Right. So yeah. So this is how you get the equality case. Are there any questions regarding this proof, how it works? So for equality cases, this is kind of true. You can just like check this out for yourself, and this implies that since so you can like sort of see that these form like every of these not just disjoint, and I should be independent as well. Yes, independent. Yeah. So for not just disjoint but independent as well. So you can see like they'll form a arpatite graph, right? You can just take, I think, the Ni's to be partitions of about themselves and just add the vertices of KR. Like I think you can just like have you can just add the vertices of KR to every partition. Yeah, I think it works out in the end. You can just have like an arpatite graph by the end, and yeah, finally you know that for all n vertex graph for all arpatite graphs having n vertices, Tn comma r must have the maximum number of edges. So the equality case basically implies. So due to edge maximality, you must have the Turan graph is the equality case. So are there any questions regarding this proof? I am audible, right?
Yeah, you're audible.
Okay, cool. So if there are no questions, I'll just move on. Okay, so the thing about the last proof, it was also kind of a local idea because we are looking at a structure inside the graph, and it was also inductive in nature. So now the proof I'm going to present it will be completely local. So it will have local ideas, and the proof is commonly called, I think the proof is called Zarankiewicz symmetrization. Okay, so here's what we'll do. So this investigates a very curious property of tripartite graphs in general. And what is that? Okay, so we'll define a relation as follows, which is simple. We'll write x sim x let's call this sim. Okay, x sim y. We'll use this notation if x y non-edge. So what happens in a complete tripartite graph is also okay. So like in the previous proof, everywhere I used tripartite, it should have been actually been like complete tripartite graph, and you can just like results in a complete. You can just, I think you can add that in. I mean, it should be you should be able to understand where I meant. Okay, so what happens in a complete tripartite graph is something like what happens is non-edgeness is an equivalence relation. What I mean by this is really, suppose you have, so equivalence relation means basically this, these conditions need to be satisfied. Right. So think about this. If there is a no edge connecting x and y, then there is no edge connecting y and x. So this is true. No edges from x to itself because it's a simple graph, true. And this, if there is no edge from x to y and there is no edge from y to z, then there is no edge from x to z as well, right? So like, think about it. Basically, if there is no edge from x to y, this means that x and y are in the same partition, right? And there is no edge from y to z, that means that they're in the same partition as well. And since it's a complete tripartite graph, you must have that y and x and z are also in the same partition, right? So this holds as well. So this is actually, do remember, this is quite nice. So like non-edgeness is an equivalence relation in a complete tripartite graph. So this has kind of an analog for a complete graph. In a complete graph, you can prove that edgeness is transitive, I think, yeah. Edgeness is transitive. Is a transitive relation. What I mean by transitive is just the third point. So like if x edge y, y edge z, these two is going to imply x edge z. This is easy to see, right? Because you like have okay, so this is not just for a complete graph. This is like for a bunch of complete graphs. So okay, I'll just erase this. I'll write it in a better language, maybe. If your graph consists, what just happened?
I think it's frozen.
Hello.
Hello? Yeah.
Yeah, I think I got disconnected. Sorry about that.
Yeah.
I'll just present 1 second. What was the last thing that was like audible or something like that? Okay.
Oh,
Yeah, go on.
yeah, nothing. Go on. I think we must like only the last 30 seconds, not much.
Okay, so what I was trying to say is like we found that if our graph is like tripartite complete, then it's then for the graph non-edgeness is an equivalence relation. So another thing I'm trying to say is like if your graph consists of a bunch of disjoint cliques, then edginess is transitive. So what I mean by a bunch of disjoint clicks is like, suppose you have I don't know, a k5 here, a k3 here, and a k4 here, and they do not have any vertices among themselves, right? So there's a bunch of clicks and they're disjoint, right? So do you feel how this relation holds true, sort of like if x edge y and y edge z, this means that they are in the same click. Here the click is sort of a partition, right? So this holds. Also note that if these kind of graphs are called like G sort of, then the complement of G is a arpatite graph of some arpatite complete actually. So do you see how this is true? Because what do you do like when you have like a bunch of clicks? Like you have, so these do not remain. So suppose you had like just uh, uh, K5 and a K3, right? So these do not remain edges anymore, and you are just connecting all of these and draw all of these and so on. So it becomes a complete bipartite graph in the number of cases. How many partitions is basically the number of clicks. So this is something we're going to use in the next proof. So any questions regarding this? I'm audible, right? It is a major scare.
You're audible, yeah, don't worry. Yeah, no question.
Okay. Yeah, okay. Let's move on. So what we will try to prove is, let's start with a kr plus 1 free graph G, which is also edge maximal. What do I mean by edge maximal is like if you add one more edge, it will result in a kr plus 1. Okay, so what we will do is we will prove that it must satisfy the non-edgeness equivalence property. So we will prove non-edgeness is equivalence relation in G. So what we basically need to prove is like if x is okay. So here this symbol denotes non-edge. Oh no.
Oh, your voice is gone again. Oh, guys, it's just not me, right? It is frozen, right?
Yeah.
Aryan, if you can hear this, your voice is gone again. It's frozen. Okay, I think he has internet issues. I'll try to get him. Just stay here for a couple of seconds. Okay, he seems to be having internet issues. We'll wait one sec. Okay, he's rejoining. Yeah.
By the way, guys, feel free to speak up and interrupt whenever, like, ask questions and stuff.
Hello.
Yeah, Aryan, yeah.
I'm really sorry about that. Like, I think there's something wrong. Okay. Yeah, I'm sorry for the delay. Okay, yeah, let's continue. Yeah, so is the screen visible? The screen is visible, right?
Yeah, it's visible.
Okay. So we'll sort of prove that what's happening. Uh, okay, my computer just hanged. Okay. Yeah, non-edgeness. We'll prove like non-edge is okay. So let this symbol denote non-edge. Like, so we will prove that if x and y are non-edge and y and z are non-edge, then z and x are non-edge as well. So how to do this is like, okay, assume
Aryan,
other. Yeah,
your screen is frozen. I think if
I
you're
am writing actually. Oh no, I'll just reshare. This is a nightmare. I'll just, let's say if I just
you unshared your screen, right? Hello.
I'm really, really sorry about this. I have no idea why this is happening. Yeah, okay. Let's it just happened again.
I'm extremely sorry for the disturbance, guys. By the way, all of you are following, right? I mean, you can like always stop him if you have questions. Like you can interrupt him. Like that. The whole reason for teaching this is that like people are not interacting that much. Um, Hopefully that will increase. Might be okay. He's DMing one sec. Yeah. You guessed correctly, his laptop crashed. Uh, he's restarting, so he'll come in a minute. So really sorry once again.
Will the last lecture on Sunday also require graph theory?
Great, right? Yeah, I think it will. So if you don't know graph theory, I can share like you can ask on the server once again, and I can share like a very like the basics of graph theory is just literally takes like 2 minutes. Like it's just like some basic definitions. You need to know what a vertex is, some edges are, etc. It's not that complicated. Actually, I think I made a handout a long while ago, which had all the definitions. I can share that too. I'll put it in resources. Okay, so just look through that. But yeah, grids should require graph theory. Some very basic stuff.
You were
Nothing.
talking about your video on the introduction to graph theory, right?
Yeah, I mean, like you don't need to see the whole video. Like I'll just share the handout. Like there's oh wait, so if you go to that video, there's like a handout shared below, right, in the description.
It's in the
Okay,
website as well.
I'll check
I guess.
Yeah, it's on the website as well. So I think like the first section had like a list of definitions you can look through. Only the first section. That's all you need. It's just some basic definitions you need to know.
Okay.
Hi. Yeah, I'm very sorry. My laptop kind of crashed. I'm just sharing.
Awesome. Yeah. Don't worry about it.
Yeah, one second. I hope I saved it. Oh God. Did I not save it? Okay. Okay. It looks like I didn't save it while starting. Yeah, give me 1 second. Okay. Yeah, I did save it. Whew. Okay. Let me like get to that part. Yeah. Okay. Finally ready. Go ahead now. Yeah. Can you see my screen? Hello.
Yep.
Okay. Cool. Okay. Let's do this. Okay. So yeah. So we'll prove that. We'll prove the non-homogeneous is equivalence relation. So for that we need to prove that if x and y are non-edge and y and z are non-edge, that implies z and x are non-edge as well. So assume not. Suppose this happens, right? So suppose you have something like x, so y and x are not. So suppose x and z are edges, right? So assuming this happens, like we'll now show that. So now we will like consider two cases. Okay, just a minute. So the main idea of the proof is like we will try to increase number of edges, right? If this happens, and how we will do it is like we will swap out a lower degree vertex for a higher degree vertex. What do I mean by this? I'll just like tell you. Okay. Okay. So like first, like consider the case where degree y is less than degree x, right? So what we will do is swap y with a clone of x, call the clone x dash. Okay. So what do I mean by this is like delete y, delete all the edges emanating from y, and just like replace it with a clone of x. So like the new y will have, the new y, we will call it x dash, will have all the edges that x is supposed to have, but there is no edge x dash, right? So suppose this new graph is called I don't know, g dash maybe, okay, or g1, let's say. So what is number of edges in eg1? So what is number of edges in g1? It is number of edges in g plus degree x minus degree y, right? So this term is greater than 0, so this must be greater than number of edges in g. So now note that if g1 has kr plus 1, this means, now think about it, if g1 has a kr plus 1, like any kr plus 1 in g1 must have at most one of x and x dash, because there is no edge between x and x dash, right? Which would imply r plus 1 click in g itself, right? So which would result in a contradiction. So what we did, we found a new graph g1 from g, which also satisfied the kr plus 1 free condition, but it has more number of edges than g, right? So okay, this add. So
can you again repeat what you mean by clone of x?
Clone of x. Okay, so suppose what we do, clone of x is so delete y and all edges from it, replace it x dash such that u x dash edge if and only if u x is an edge. So that's more formal if you like it. Basically, the new y will have edges with all neighbors of x. Does that make sense? So it's basically a clone of x in some sense, right? So like it will have edges to all vertices that x has edges to. So yeah, so we found that g1 is kr plus 1 free, but more edges than g. So this is a contradiction to edge maximality of g, right? So basically this cannot happen, sort of. So this case is done. So the next case is kind of degree y is at least degree x. So now note that this implies that degree y must also be at most degree z, right? Otherwise, repeat case 1. So what we will do is like similar, basically. We'll just swap out the lower degree with a higher degree. Replace x and z with clones of y. Right. So call the new graph G2. What is EG2? So EG2 is basically EG1. So you are deducting degree x number of edges and degree z number of edges, but you are deducting the xz edge twice, so you add 1, right? And you are adding in 2 degree y number of edges. So this term, because of this condition, is greater than 0. Okay, so is like greater than 0, the entire term basically. This is greater than 0. So the entire, so finally you get like E of G2 is greater than E of G, right? So then again, we have the same problem. So if we noted that EG2, so basically G2 is KR plus 1 free. This is the same thing, right? Because if the new clones are, let's say, Y1 and Y2, then any KR plus 1 can have at most one of Y1, Y2, and Y, because they do not have edges amongst themselves, right? Okay, so G2 is KR plus 1 free, and E of G2 is greater than E of G. So again, contradiction to edge maximality. So any questions regarding this proof? So we proved the claim, right? So this basically, so this claim is going to imply that G is k-partite, not r-partite necessarily. Note that is k-partite for some k-partite complete for some k. So are there any questions? Also, k is obviously at most r, because otherwise there would be r plus one click, right? So any questions regarding this? I'll just move on to the next part of the proof there. Also, I might need maybe 5 to 10 minutes extra because I plan to cover a bit more. So now note that the proof isn't over. So proof not over. We need to make sure of two things. That's like one of them is like not too many parts or too less parts. Another one is size of the parts. And how do you do that? That is like really stupid sort of. If you have like, suppose these are the partitions, and if you have something like a lot of vertices here and less number of vertices here, then you just like do this, like as simple as that. And you sort of like just convince yourself this increases edges. So basically, even if you like try to do this thing, this is basically, it'll boil down to the fact that we like saw earlier, that like if G is r-partite complete and has n vertices, then the G having max edges is the Turan graph. So yeah, so basically the proof boils down to this fact really, which you can prove by MGM as discussed previously. So yeah, so does anyone have any questions regarding this proof? So this was Zarankiewicz symmetrization. The swapping idea is going to come up a lot. Basically, either to increase degree or to decrease degree or whatever. So if there are no questions, then I'll move on to the next proof. And just see the chat rooms. Okay. No questions. I'm audible, right? Uh-oh. I'm audible, right? Hello?
Yes, yes, you are audible.
Okay. Cool. Okay, so the next proof is going to be the probabilistic method proof. So proof 3. This is going to be probabilistic method. So this will not directly give you a proof for Turan's theorem. This will only prove that E of G, if G is KR plus 1 free, is at most n squared over 2 by 1 minus 1 over R. But it's a proof for the R divides n case. Okay, let's do this. So what do we do in probabilistic method problems in general? We introduce randomness in a non-random situation, right? Okay, so now think about it. What we are going to do is like we will build a click S, right? And we'll compute its expected size. Okay, what do I mean by that? Okay, so like how we will build that click. So the algorithm for building the click is as follows. First, you'll just pick a random permutation of the vertices. Simple. Now, if some vertex isn't already in B, and if it is neighbors with all the elements already present in V, then we will add it to the, then add V. So what does this mean is like you choose the first vertex, right? Think about it. So you choose the first vertex, and then you choose like, and then you look at the next vertex in the permutation, or you can think about it like this. Otherwise, other words, choose first vertex, delete all non-neighbors, right? Choose all first vertex, call the vertex v1. Okay, choose next choose next neighbor in order. So like so among the remaining vertices, all are neighbors of v1, right, by the condition. So you choose the next neighbor, choose next neighbor, call it v2, right? Next, what you do is like delete all vertices not in n of v1 cap n of v2. So in other words, which is not a common neighbor with v1 and v2, right? So what this ensures is basically that S must be a click when the process ends. Do you get the thing? Like basically you are adding a vertex to the set if and only if it is neighbors with all the others already present inside, right? So you can like think about it. It has to be a click, right? So now we will try to calculate the expected size of the set S, right? So for that we'll like just assign indicator variables to each vertex. Will like be v belongs to S and 0 otherwise. So now you know that expected value. So now recall that the expected value of S has to be less than at most R, right? Because you cannot have R plus one sized click. So R is at least this, and then this is basically summation over V belongs to V. This is just linearity of expectation, right? So this is basically summation V belongs to B, probability that the vertex V belongs to S. Now, what is probability that vertex V belongs to S? Think about it. It's basically something like, consider a vertex V, right? And consider all n minus 1 minus degree V of its non-neighbors. So, okay. Consider V belongs to V and all n minus 1 minus degree V of its non-neighbors. Non-neighbors basically means those who aren't adjacent to V, right? So V can belong to S if and only if it appears higher as in earlier, sort of higher, earlier, whatever. Than all of its non-neighbors. Convince yourself that this is true, because in all other cases you will find that V kind of gets killed earlier, right? Because if it doesn't like if it is sort of sniped by another non-neighbor, then when we execute the algorithm on that non-neighbor, it will kind of kill all. So suppose V comes after a non-neighbor of its, call that X. So like V and X is not an edge and X comes before V. Then when you are running the algorithm on X, right? So then like X is going to get like you're going to kill all non-neighbors of X, which is going to include V as well. So since all the permutation we initially chose was like completely uniformly random, so this probability is just 1 over n minus degree V. Why is this n minus degree V? Because you're taking n minus degree V plus 1, no, sorry, n minus degree V minus 1 non-neighbors and plus V itself, right? So okay, this color sucks. Okay, let's move on. Okay. So now we came to the conclusion that R was at most expected value of S, which was equals to V belongs to P expected value of XV, which was just V belongs to V, probability that V belongs to S, which was, as we just found, V belongs to V, 1 by n minus degree V. Right. So again, we will just use Jensen on this because you can just check that this function is convex, right? Then this becomes basically 1 minus summation of degree v belongs to b by n, and you'll have an average term here, so n term here. So this becomes basically n by n minus, let's say the number of edges was m, right? Oh, okay, shit. So this becomes 2m by n. So you can just rearrange this to get so m is at most of, I'll just move on to the next page. So you can just like sort of rearrange this to get m is at most n squared over 2 by 1 minus 1 by r. Yeah, so any questions regarding this proof? Any questions regarding the proof? If not, I'll just move on. I'll probably take maybe 10 minutes more. Sorry about that, to make up for the time. Okay, so again, like, note that this proof doesn't tell you anything about equality. So what we saw in general in all these proofs was that if you have a local idea based proof, right, local is going to give you idea about structure of the equality case. So what I often do while I'm solving a extremal graph theory problem is try to find the equality structure first, and then try to equality graph first, and then try to find a special structure in the graph that is really highlighted, right? And then try to like do something from there. If you are not able to find the extremal graph theory, the extremal structure in the extremal graph, then well, it sucks kind of, because otherwise it's going to be hard to solve the problem in general, right? So if you can't find it, it's kind of hard to solve the problem, in short. But then one thing you can do is like you can be very smart, and you can like just think of the special structure. For example, you might have a feeling that independent sets are going to be important in the problem, or a let's say something like a maximal matching is going to be important in the problem, and start working with it. Although I'd say this becomes much more prominent if you just know the answer, sort of, if you know the equality case, right? Then those ideas are much more motivated. So yeah, so local gives you an idea about the structure of the equality graph, and global ideas is sort of more algebraic. Okay, so this was about, okay, so I'll talk about another lemma, sort of. So this was all about Turan's theorem. So the next I'm going to talk about is Zarankiewicz lemma. I think I did not pronounce that right. I'm sorry about that. So this is also like quite important sometimes. So if G is kr plus 1 free, then there exists vertex V with a degree of V at most r minus 1 by Rn. Okay, so this is what Zarankiewicz Lemma tells you, that basically if you have an r plus 1 click free graph, then you will have a vertex whose degree is not too large, sort of. You can think about it like that, not too large max degree. Not necessarily max degree, not too large degree for all vertices. This is one way I think about it. Okay, so the proof for this is really like sort of a very direct proof in some ways. What you do is like, yeah, give me a second. Yeah, so like let's start. So assume not, obviously, because what else? Okay, so there's the proof. So assume not. So I'll just write d of v instead of degree every time. Okay, so d of v is always greater than, let's say this quantity is x, right? The degree of x for all v belongs to v. So this is given to us, sort of, right? So now pick any vertex v1, right? You know that it has a neighbor v2. So basically the idea of the proof is like, if the condition doesn't hold, we can sort of build a kr plus 1, right? How? I'll just like, you can sort of calculate n v1 cap n v2, and as you add on more vertices, n v1 cap n v2 cap n v3 cap, so and so on, right? So like the the intersection of all the neighborhoods of all the vertices that we have till a point, and you can find that it's still greater than 0, so you can find a vertex inside all of the neighborhoods, which means that you're basically kind of building a clique, sort of. If you just do the initial calculations, so nv1 cap nv2 is just d of v1 plus d of v2 minus the intersection, minus the union, that is n of v1 cap n of v2. Now this is given to be at most like 1 plus x, right? 1 plus x, there's 1 plus x, and this is obviously at most n, because n vertices, right? So n, and you can just check that this is greater than 0. In fact, this proof kind of carries over, like you can sort of inductively define, so the main claim is that you can find vk belongs to union y equals to I think 1 to k minus 1 n of vi inductively for all 1, 2 greater than k greater than r. So how to do this is like, I think something like, if you have done till, if there are any questions regarding the proof, please do feel free to ask. I'm kind of rushing through it, I understand, and sorry about that. I'm out of time already. If you have done till like I think j minus 1 vertices and want to add okay, so let's say up till j vertices, and you want to add j plus 1th vertex, then you need something like this to be 0, right? So basically you want to find a vertex in all of the neighborhoods, all of the j vertices neighborhoods, right? So, and you can just like and this comes out to be basically you are writing you will write like how many j degree vi terms, and then some terms due to pi, right? So kind of work this out yourself. It will come out to be at least at least degree vi, which is like 1 plus x. So you will write 1, so you will write this basically, and all the terms due to pi will be at most n, and they will have j terms in total. So you can just like work this out yourself, maybe write it out yourself. This isn't very hard, and this is like greater than 0 for all j at least r. So basically the best thing about the best thing about x, the way x was chosen is such that the equality is the way x was chosen, the equality is, the condition sort of is just true for the j equals r case. So you'd have to do something like, I think r times 1 plus x minus r times n is greater than 0, or something like that. You can just prove via definition. Yeah, I think that is all about Zarankiewicz's lemma. Is there any question regarding this? Any doubts regarding this proof?
No, but what do we get if this value is greater than 0?
I can't hear you. Can you come again?
I asked, what do we get if this value is greater than 0 for k equal to r?
Okay, so I'll just review the proof once. So what we did was like, the idea of the proof is to build a r plus 1 clique, right? So how do you build is like, you start with a vertex, right? Call that v1. You have a neighbor of v1, call that v2. Now what we will do is like we will find a v3 which is which is adjacent to both v1 and v2. In other words, v3 belongs to the intersection of neighborhood of v1 and neighborhood of v2, right? So, and then again we will find a v4 which belongs to the neighborhoods of v1, v2 and v3, right? In other words, to find such a v4 or v5 or so on, a vk in general, you need to have the intersection of neighborhoods of all the vertices till then we have chosen to be greater than 0, right? If the cardinality of the intersection is not greater than 0, then you cannot choose the next vertex. So that is basically the idea of the proof.
Right.
Okay, and x is given in such a way such that the proof works out, sort of the calculation sort of work out. Okay, so the next thing is, I think, kind of really short. I'll just talk about Ramsey numbers. And this is very short. This is going to take like 5 minutes. So Ramsey numbers is basically, call it RST. So the definition goes like, suppose a Kn is bicolored with red and blue. What's minimal n such that no matter coloring, this is bad language, but I hope you understand. Such that no matter so that this given any coloring, I think I'll write just like that. That given any, you can find a red KS or a blue KT. So this is basically the definition of our Ramsey numbers. I think I defined them right. Yeah. So it's a minimal n such that whenever you have any bicoloring in red and blue, you can find a red KS or a blue KT, right? So we'll just like mention 2 to 3 theorems on this. So first theorem is basically very easy. That is Rn, 2 equals n. So this is like very easy, right? Like if you have a n gone, right, then if you aren't like not just n gone, like that is bad language again. So if you have a n kn, right, if you aren't coloring to like you aren't, suppose there does not exist any, suppose there is a red u and a, okay, this is, so okay, I'll just mention sorry, I'm kind of hastily going to this. So when I mean like a kn is bicolored, I mean to say edges are bicolored, right? Just mention this to avoid any problems. So I mean to say edges are bicolored. So like suppose you have a k, so the theorem I'm trying to prove is like R of n, 2 is n. So the counter example is easy. I just say try to counter example is easy. Try to figure that out by yourself. It's just, I think, yeah, it's easy to prove. And for kn, you just have like, if you like color one edge blue and other edge red, then you yeah, if you have like an edge of different colors, two edges of different colors, then a k2 is just like one edge, right? So that condition is met. Otherwise you just end up with a red kn or something like that if you are not having any blue color at all. So Rn2 equals n is easy. The next thing is, I think, yeah, R3, 3 is 6. So this is classical, and I'll omit the proof for this. This is just a, I think, standard pigeonhole principle exercise. The only real theorem that I want to discuss is this. If s, t is greater than 2, then RST is at most Rs, t minus 1 plus Rs minus 1, t. So the proof for this is basically just assume not, right? Suppose Rs, t is greater than Rs, t minus 1 plus Rs minus 1, t for some s, t greater than 2, right? And let this value be n, right? So now consider a bicoloring of Kn, right? Pick any vertex U or V, let's say. Okay, so let NR denote red neighbors of V and NB denote blue neighbors. What do I mean by red and blue neighbors? They are connected by red and blue edges respectively, right? So now you make the following observation, right? Think about NR, right? It can have no blue KT among itself because of condition. So if it has a red KS minus 1, what happens? Then NR union of what is that vertex V gives you a red KS, right? Which is a contradiction. So this can't happen. So what this means is basically NR is must be less than must be at most basically RS minus 1 comma T less than minus 1. Okay. Similarly, you can prove that NB is at most RS comma T minus 1 minus 1. Similar logic, right? So then basically you have a easy contradiction. So like you know that NR plus NB on one hand this must equal n minus 1 because it's like all the other vertices, right? It's a complete graph, so it's connected to all the other vertices. And NR plus NB is also like at most RS minus 1 comma T minus 1 plus RS comma T minus 1 minus 1, and this is basically n minus 2. So you get something like n minus 1 is at most n minus 2, and this is a contradiction. So yeah, this proves the theorem. So any questions regarding this? Or throughout the lecture, if you had any problem to understand?
Actually, I had joined late. So, did you discuss the practice problem that you sent today?
No, I couldn't find time. That I'll do that tomorrow. So today's class was really a theory class. Okay. Are there any questions in general from the talk from today's session?
I don't have a question from the talk related to the talk, but I have a question in general.
Okay, I'll try to answer it, or you just maybe okay, go on.
Yeah, so I'm not very confident about my graph theory because I just started it a few days back.
Oh.
So like, yeah, so I was advised to study from the handout from the introduction to the graph theory class that was taken. So after that, can I just jump onto the problems that were done today, like the problem set that you sent?
I think the problems I sent are quite hard, so can give them a try. Obviously, I mean, do spend some time over all of them if you can, but I think they are quite hard problems in general. So like, don't be demotivated if you can't solve any. So that is kind of the point I'm discussing hard problems, because they'll show you a lot of ideas.
So does that handout already has some problems in it, so that like I can at least get a basic idea of how the problems are at a simpler level?
Oh yeah. There are like many easy graph theory problems and all those handles, so don't worry about that.
Yeah, I think there should be enough easy problems. Maybe I'll mention a few in the handout as practice problems, which I'll not discuss in class. Maybe I think you should be able to do maybe the first two problems are I think doable. The rest are hard. Yeah, the handout or the problems that I sent out.
Okay.
Okay. Any other questions?
Oh, I'll end the recording then.
Yeah, sure.